Hello. Okay, we're going to talk about kind of the relative strength of intramolecular forces, focusing on London dispersion forces. All right. So let me try to make this make sense to you. I'm going to share my screen. And recall that what we were previously talking about were intermolecular forces. We said that they are the forces that hold molecules together. They are not within a molecule, as that is a chemical bond. That is an intramolecular force. We are talking about intermolecular, like an interstate connects states. We are connecting molecules, holding one molecule to another. They are present in solids and liquids and not in gases. We said that there are three types. There are London dispersion forces. And we said that these exist among non-polar molecules. Not within them, those are covalent bonds. Among them, all right? And we also said that we have dipole forces, right? And those exist between, I left that word out, between. These exist between polar molecules. And then we said that there's a special type, which is hydrogen bonding, right? It is a special dipole force, even though it has the word bond, it is a force. And we said that it occurs when hydrogen, very small and not very electromagnetic, is bonded to nitrogen, oxygen, or fluorine due to their small size and their extreme electronegativity, resulting in an increase of partial positive and partial negatives, and a stronger attraction. That was what was discussed in the last video. In the last video, we also said that these are the weakest and these are the strongest. However, that is not always the case. It is simply the general trend. But we observe that there are disruptions to this trend, and we have determined what is causing the disruptions. The disruptions meaning that London dispersion forces are not always, therefore are not necessarily, weaker than dipole forces and hydrogen bonding forces, just most of the time. In general, they are a weaker force, but there are factors that can cause them to be stronger, and that's what we would like to discuss. So when we talk about our relative strength, let us begin with our, let me get back up here, apologize, trying to find a good color. Let us begin with our London dispersion forces. Recall, we've got purely nonpolar molecules. So what that means is there are no permanent dipoles, right? There's not a permanent dipole. There's not a permanent partial positive, partial negative end. However, they can be temporarily polarized. Temporarily polarized, or polarization, can and does occur. Okay? Larger electron clouds relate to a greater polarizability. And then next is a greater polarizability. Relates to a stronger attraction, a stronger London dispersion force. All right, so let's try to simplify that. The strength of London dispersion forces is determined by the polarizability. The polarizability is determined by the size of the electron cloud. All right, such that nonpolar compounds that are larger or contain larger atoms are more polarizable, and therefore they have stronger London dispersion forces. All right, so if we were to compare our halogens, fluorine, chlorine, bromine, iodine, we see that the size increases, right? We talked about atomic radius last semester. We see that the size increases, therefore size of electron cloud increases, right? Therefore, this all makes sense. Therefore, polarizability increases, right? Polarizability increases. Everything we just said. Therefore, London dispersion forces increase in strength as you go down. And we can have evidence of that. And the evidence is this. Fluorine is a gas at room temperature, standard conditions. Remember, gases have no IMFs. They don't have any attractive forces. Gases, chlorine is also a gas, no IMFs, no IMFs. Really small. Their electron clouds are not really polarizable. And in result, we see gases where there's assumed to be no IMFs. However, bromine now is larger with a larger electron cloud, more polarizable, and look what we have. We've got a liquid. It is a liquid at standard conditions. So this has some weak IMFs, right? There are IMFs present now. And iodine, which is underneath bromine, has an extra electron cloud, therefore is more polarizable. In fact, is a solid at room temperature, okay? So we see that as that size increases, right, we get a larger electron cloud. The molecule itself has electrons that can be greater temporarily. They're more affected by an electronic charge or a magnetic field. And we get stronger IMFs, as I just said, which is evident by the state of matter that these halogens are in. Okay, we could look at that another way. In class, I would show you a sample of methane. It is a gas. However, if we increase the size of this hydrocarbon and we get to butane, we get to C4H10, we now have a liquid, all right? So we go from small, not very polarizable, very weak IMFs, right, to bigger, somewhat polarizable, and stronger IMFs. Right? There's still liquid, but then if we get to like C, I don't know how many C's we have to get to, but at some point, say it's like C22H46, we have a solid. We've got like wax. That might be wrong. Okay, my equation might be wrong. But you see much bigger, much more polarizable. And what we see present is a solid. So we've got the strongest of the IMFs. So what we're seeing is how the structure, the size, affects the polarizability, which in turn affects the strength of the intermolecular forces, once again, which is evidenced by the state of matter present in relation to the size of the molecule. Now, and that's it, right? That's all I'm going to tell you about those London dispersion. And if you were looking at something like HCl versus HI, right? We could talk about electronegativity. But then we've got various factors. We've got size, we've got electronegativity. But these are polar, right? These are polar. Therefore, they have London dispersion forces and dipole-dipole forces, right? We assume those dipole-dipole forces here will be stronger than the London dispersion forces caused by any temporary polarization that's occurred. These molecules are already, they have permanent dipoles, right? And if I had to predict between HCl, who's got a partial negative on chlorine and a partial positive on hydrogen, and HI, which has the partial negative on iodine and the partial positive on hydrogen, my prediction would be that this one would have the strongest of the dipole forces. And my reason would be because chlorine is more electronegative. Now, I see another play here. Strongest because chlorine more electronegative. We could start thinking about the size effect of chlorine and iodine, and that could be in consideration. So if there was a discrepancy to my prediction, if it didn't hold true, I would then relate it to, well, iodine is bigger than chlorine, so maybe that trumps the being more electronegative here. Okay. And then, you know, just notice when you have compounds such as CH3OH, right, or C2H5OH, we've got London dispersion in both, because remember, all molecules have London dispersion. And notice right here, that's your hydrogen bonding, right? You've got the oxygen attached to the hydrogen, creating that really intense partial negative, partial positive due to the small extreme negativities, the small size and the extreme negativities of both atoms. Here you've also got hydrogen bonding. But which one overall would we predict to have the strongest forces? Well, I would predict this one too here, because the base of that hydrocarbon is larger. So this is more polarizable. So we have hydrogen bonding in both. However, the base here is larger and more polarizable. So my prediction would be that this molecule would have the strongest IMFs in relation, in comparison to the small methanol, with methanol, ethanol, okay? All right.